Hey AP Chemisters, this is Mrs. Vanderwall with another edition of the Blankwall video series. My goal for the Blankwall sessions for this weekend is to finish up section 15.4, which is the titration of the weak acid with a strong base or a weak base with a strong acid. And then continue on in section 15.5, which is indicators, and talk about the basic concepts of section 15.6, which is KSP solubility product. My hope is that you will actually work through these problems first and then go over the answers with me on this Blankwall series. So let's get started. We left off about titrations of weak acids and strong bases. We are actually working on filling out this particular graph, and we want to continue doing that. And we have done some of the problems already. So we figured out 10 mils of the sodium hydroxide, 25 mils, and that's where we left off the other day. And that was so exciting because that is where you met the halfway point. And at the halfway point, we have moles acid equals, the moles base used up, and we have the equal number of moles of your weak acid and its conjugate base. Because of the HH application, that is also where pH equals pKa. And hopefully you're looking at that for your lab that we just finished. So go ahead and work on part D when 40 mils of 0.1 molar sodium hydroxide has been added, and then we'll check your answers. So give yourself a few minutes and then come right back. Okay, hopefully you had a chance to work out this problem. We had to convert everything into moles. So we started out with our original 0.005 moles of acetic acid. We are going to titrate it with 0.004 moles of sodium hydroxide. Set up your BCA table so that you have 0.001 moles of acetic acid left. You used up all your sodium hydroxide, but you've created 0.004 moles of the acetate ion. So now we have, in a sense, our buffer solution. We have the acid, the weak acid, and the conjugate base. And now we can apply this with the HH equation. So here's my HH equation. Notice how I had to convert everything into molarity of the base, molarity of the acid. Notice that the amount of liters keeps increasing as I titrate. And so you end up with the pH of pKa plus log of 4, and that is your 5.34 pH. So our pH is, of course, getting larger as you add more and more sodium hydroxide. How does this look on our graph? So let's go ahead and go to our graph. Let's plot our point, and this is what we have so far. You notice how it is starting to go up, but it's leveling off a little bit. Now go ahead and see what's going to happen on the next one, where we have 50 mils of 0.1 molar sodium hydroxide. Think about what this is special here and how we're going to treat this particular case. So why don't you go ahead and pause this, and we'll come back and see how you did. Well, holy cow, look what happened here. We have what we call the equivalence point. This is where you have moles acid equals moles base, and notice how they neutralize each other. So at this point, think carefully on what is in your beaker right now. You don't have any more of your weak acid. You don't have any more of your sodium hydroxide. The only thing left in your beaker is your acetate ion and your water. That's it. So how do you set up, in a sense, your ice table right now? Well, think about it. This is what you have. You have your base and your water. So now you're going to create your weak acid with hydroxide. Now, what changes here? When you go on and you figure out how many moles of everything you have, what molarity you have, consider this. You start with your base. You start with the acetate ion. So instead of finding the HH equation where you find pH equals pKa plus log of B over A, you actually got to start with what's POH, because look at here, you are creating your strong base. And so you have to go your POH when you go through this. So let's see what happens here. Go ahead and pause this and work out the rest of the problem while I do that too. So hopefully the first thing you did is that in your ice table, you need to have molarity. So we had to go back and calculate what the molarity of your acetate ion is. We have 0.005 moles of the acetate, but you also have a total volume of 100 milliliters, which is 0.1 liters. So our initial molarity of acetate is 0.05. So we'll go ahead and write that in. All right, so I found the molarity of the acid ion. I'm setting up my ice table. I define X as being my weak acid and my hydroxide. So I'm setting up here Kb, because acetate ion over here is a base, is equal to X squared over 0.05 molar. But wait a minute, what do I need to find? I don't know Kb. I need to find Kb. So here is Kb. It's equal to KWKA, which is equal to 1 times 10 to the negative 14th over 1.8 times 10 to the negative 5th. And so that's your Kb value. So now I know what my Kb is, and I can solve for X. So X squared is equal to 0.05 molar times your Kb. Solve for X, and we can find it here. So X is equal to 5.929 times 10 to the negative 6. Now that's all and good, but what are we trying to find? We're trying to find pH. So here we go. We're going to find X is pOH first. Here it is. And so it's your 5.27. And so pH is equal to 8 point. Somehow I'm losing it here. 8.72. So what can I do with this? Let's go back and plot our point. So we'll go back here, go to our graph, and plot our point. And here it is. Wow, it shot right up. With 10 more mils, it went pretty high. And remember what we call this. This is our equivalence points. This is where moles acid equals moles base. And then what else did we say up here in our notes? It says that the stronger the basic anion, meaning your acetate ion, the higher the pH of the equivalence point. That the equivalence point is always going to be greater than 7.0, and we see that is true here. It was 8.72. So I tell you what, why don't you go ahead and do the next one. We'll stop and pause and see where that leads us. So go ahead and work out, really try the rest of this problem right now. Okay, so in the next case, we have 60 mils of 0.1 molar sodium hydroxide has been added. And notice what happens. We're going to use up all of our weak acid. We're going to have leftover sodium hydroxide, and we're going to create some of our weak base, the acetate ion. Now, think about what this means. We have two bases in our solution. So we could have something like the equation here. Whoops. I'm not sure just what happened, but I had a blank screen all of a sudden. So anyway, we could have this situation where we have just the weak base. And notice if the weak base is in there, we have sodium hydroxide. And notice that we could go through here and do our calculations, but do we really need to do that?
Please, Julie Matthews, you are muted. Football stadium, please.
Sorry about that. And the answer is no. We really don't need to go through any more ice tables. We really don't even need to do the HH equation, because in our solution we have a strong base in the hydroxide and a weak base in the acetate ion. The strong base is what's going to be the predominant species, and our case is almost already solved here. We know the hydroxide concentration. We can solve for its molarity. 0.001 divided by 0.110 is 0.0091 molar solution. We can find the pOH, therefore the pH is 11.96. So another 10 mils is a huge jump in pH. You probably saw that in your lab on Friday, where you were working with a weak diprotic acid, and even a couple drops could make a huge difference. Imagine at this point what 10 milliliters would have done to your titration curve. So let's see what this titration curve looks like. And here at 60 mils, I tried to put about 11.1 whatever up here. So notice our curve is going kind of crazy. Let's see how this whole thing ends, and go ahead and quickly do the very next one when you have 75 mils of sodium hydroxide added. Then pause it, come right back. All right, so here's the last one. You put the acetate ion, or the acetic acid in with sodium hydroxide. Again, your acetic acid is your limiting reactant. It runs out first. You have excess moles of sodium hydroxide. I'm not even too worried about how many moles of the acetate ion I have, because even though it's a base, it's such a weak base that the hydroxide is going to be the predominant species. So I'll find the molarity of the hydroxide. You'll see I did the work over here. I have 0.0025 moles. Notice that my volume keeps increasing too. I have to count for how many additional mils I add to it. So it ends up being my hydroxide concentration is 0.02. Shame on me, I forgot my M for molarity. I found the negative log of that, I found pOH, and therefore pH is 12.30. And so let's finish off the titration curve here. I put that last curve up here, at least I tried to, and here is my titration curve. Now, if we had slowed things down and did things drop by drop, we would have been very interested in seeing, let's say, this part of my graph right here and see how it really works. So it's probably pretty steep up here, and then it levels off again. It'll look a lot like your curve in your lab from Friday. So what I'd like you to do now is actually do problem 9 from scratch. I will not stop. I will not interrupt you. I want you to do the entire problem number 9. When you are done, click back on this again, and then you'll see how you did. So do the whole thing first, guys. Don't wait for me to show you how. Figure it out on your own first. Well, I've discovered one thing about doing this. I still don't leave myself that much room. So hopefully you can see what I was trying to do. For this one, you start with the hydrogen cyanide acid, or excuse me, cyanic acid and the hydroxide. And then you notice that you have leftover HCN here. You used up all your hydroxide. You have leftover CN minus. Notice I had to then convert it to molarities here. And once I have the molarities of both the HCN and the cyanide ion, up here is where I plugged it into my HH equation. I found the pH is 8.48. At the halfway point, this is the exciting stuff. Look what happens. You have identical amounts of moles of the HCN and the cyanide ion. And so notice that their molarities are identical when I came up with the molarities. And how did I come up with the volume? Notice I found molarity moles over liter is that's how many. I'm sorry, it should be 0.10 molarity. That's my mistake. Let me fix that. Put a little M here, not an L here. That's an M. All right, and then that told you how many liters you had, and you could then go ahead and solve. Now, what's so exciting about this? Notice that the log of the same number, 0.033 divided by 0.033, that log of 1 equals 0. So your pH is equal to the pKa. And then finally down here at the equivalence point, that's when moles acid equals moles base. So you end up with no HCN and no hydroxide left. You end up with 0.005 moles of cyanide. Notice how I then had to convert moles into molarity to put it into my ice table. I had to figure out my volume the same way as I did before. I know how my moles of hydroxide used. I know the molarity of my hydroxide used. I can find my volume, and it's cumulative. Therefore, x squared over 0.05 is your KB. Therefore, we have x is equal to 8.9 times 10 to the negative fourth. pOH is equal to 3.04, and pH equals 10.96. So once again, notice that the equivalence point is much higher than 7 because we have probably a much stronger base. So the significance of the halfway point, where pH equals pKa. And again, it's the amount of acid necessary, not the strength, that determines the equivalence point. The pH at the equivalence point is affected by the acid strength. So that concludes this portion of the blank wall. We finished up the problems in the book, or excuse me, the problems here. Now you can do the problems in your book. And go ahead, and when you are done, go ahead and find the blank wall for the next section. Bye.